Okay, so atomic structure. So atomic particles, protons, electrons, neutrons. Protons from the nucleus, electrons, orbitals. Yes, this I understand. Okay, there are various models for the atomic structure. For example, we have L, 7 and 3. 7 is the mass number, which is A. 3 is the atomic number, which is Z. What do you... Why is this not connecting? Oh. Okay. Are already connected? Okay. Now let's try. I got it. Wait, what? An app is needed too. Excuse me. I connect this. An app is not needed. Just okay. I'll try to switch it off. I think it's kind of dead. Okay, so the mouse is not connecting. And it's driving me mad because I've connected the... Have I? It's kind of dead though. It's okay. Oh, it might be connected to my... Okay, okay. It was connected to my phone. That's all. Okay. Now. Yes. I think I've done it. Yes. See that? And the mouse. Oh my god. Oops. Why is it going on YouTube? Hold on. I'm gonna finish this one. Okay. Isotopes. Same number of protons but different number of neutrons. Isotopes. They have similar chemical properties because they have the same electronic structure. They have different physical properties due to the mass. Time of flight determines isotopes that are present, identifies elements, vacuum, so that air particles don't get ionized or registered. Okay, so this is electron impact is 2. Oh yeah, I wanted to check this the other day. What does it mean by having a low I think it is what. Okay, so if it has a low. But what? Okay. I'm gonna ask ChatGPT because I don't fully understand and I want to. So. Okay. What does it mean by low formula? By low formula. Why does it take ChatGPT this long to load? Okay, whilst I'm waiting, I guess I can just read the rest of my notes. Okay. Electron impact, vaporized sample, detected at low pressure. Okay. So, formula mass. Okay, yeah. Okay, so I was right then. Okay. Electron gun has high energy electrons. The sample knocks off outer electron. Positive ion forms different charges. So this is the equation. Okay, my goal for today is to do all of the atomic structure. Electrosphere ionization. Samples dissolved in a volatile polar solvent. Yes. Injected with a fine needle. Yes. Given a fine mist or aerosol. The tip of the needle, high voltage. Tip of the needle, sample molecule gains a proton. Solvent evaporates and H goes towards the negative plate. Okay, this I also understand. Number 2 is acceleration, because first is ionization, which is that. Positive ions are accelerated by electric field, yes, and have the same kinetic energy, so it means that it is constant. Now we have an equation, which is V equals the square root of 2K divided by M. So yeah, that's good. Then number 3 is the flight tube. Smaller ions travel faster than those that are bigger, but they still have the same kinetic energy. And that's where I finished. So, where's atomic? Okay. Okay. Okay, this bit I did. So I'm just gonna say, okay. Yeah, this is the bit where I got up to. So go up to the flight tube. And use whoops. Toggle pen. T equals D square root m over 2ke. So I don't know which one you're supposed to really remember. Is this like if you need velocity, then it's 2ke. But then if you need that one's gonna t. If you need time is always in seconds. So time is always in seconds. The distance is always in meters, isn't it? Yes. The length, distance, is always in meters. And velocity is just ms. Okay. The last one we have, which is number 4, is something called detection. And hold on. The ions reach the detector and generate a small current. So when the ions reach the detector, a current is generated. Okay. Which is fed to a computer for analysis. The current is produced by electrons transferring from the detector to the positive ions. Okay. Which is given to the computer for analysis. And then what's the next bit? Oh yeah, how the current is formed. The current is formed by the electrons transferring from the detector to the positive ions. Okay, the size of the current is proportional to the abundance ratio. So current is proportional to the abundance of species. Oh, put spices. There's no species. Well, can be measured. So it's measured by m/z, which is the mass to charge ratio, and abundance. Sometimes 2 electrons may be removed from a particle, forming a 2+. Have an MZ of 12. Wait, I'm pretty sure I have a periodic table somewhere. Do I? I don't. That's rather interesting. Well, oh, let me put periodic table A level. Why is it offline? I just need a periodic table. So if hold on. It's not just the same thing. Oh my gosh. I just got the periodic table. Where's it gone? It's actually not real. Finally. So they said if example okay, where's MG? MG's here. But it's hold up. It said sometimes 2 electrons may be removed. 2 electrons. Two electrons may be removed from a particle, forming 2+. Forming 2+ ion. A 2+ ion. So 24 Mg 2+ will have a charge of 2+, and you'll have an MZ of 12. Wait, my brain's not braining. What is going on? Wait, so MZ of 12. So what difference has it made? 2 electrons may be removed. What? Okay, wait. Sometimes 2 electrons may be removed from a particle, forming a 2+ ion. Okay, this I understand. That's because it lost 2 electrons. Oh. Okay. MZ is the protons, number of protons, I think. So, but it would just have a 2 plus. Okay, it's fine. I'll do some questions on it. Okay, so there's a example of a maths question. I think I'll just print it out and stick it on my page. But what happens is a sample of nickel was analysed and one of the isotopes was found, 59 Ni. The ions were accelerated to have that much joules of energy, kinetic energy, and travel through a flat tube that was that many meters long. How long would one ion of 59 Ni plus take to travel along the flat tube? Okay. So we have the equation, what was that again? T equals D square root M over 2ke. So do we have T? Wait, what are we looking for? How long? We're looking for the time, so that's perfect. That means D is 0.8000 meters, and it's meters, which is what we want. Then M, what's M? M is the mass, right? So, well, actually, we don't have the mass, so we need to find it. So we know that it's 59 divided by Avogadro's constant, which is 6.022 times 10 to the power of 23, and then we'll have to times that by 1,000. And then we have Ke, which will be times by 2, and we have 1.000 times 10 to the power minus 16 times 2. Okay, I'm going to work out the mass first. So 59 divided by 6.022 times 10 to the power of 23. And then I have to times it by 1,000, right? 1,000. Okay, that looks fairly correct. Is that the same? Oh, I didn't get minus 23. Oh my gosh. Okay, I'm going to try again. So 59. Oh, maybe I'll put them in brackets. I think that's better. Divided by 6.022 times 10 to the power of 23. There we go. And then we times it by 1,000, which gives us do we times it by 1,000? Divided by 1,000. Okay, this is what we got, and then we divided by 1,000 again. Oh, we divided by 1,000, not multiply it. Okay, that's one mistake that I did, but I shouldn't do that mistake again. So I'm just gonna make sure I don't do that again. So I got 9.797 times 10 to the power of minus 26, which here 9797. Yes, that's correct. And now I do 1.000 times 10 to the power of minus 16 times by 2, which gives me 2 times 10 to the power of minus 16. Now if I put it into the equation, so D is 0.8000, and then I multiply it by the square root of 9.797. I should probably put some brackets. I'm actually scared it's gonna mess up. Times 10 to the power of minus 26 bracket, and then divided by 2k, but I already did it, so it's gonna be 2 times 10 to the power of minus 16. Okay, I got 1.77 times 10 to the power of minus 5. There's no way. Yes. Yes. You know, I feel like a genius when I get something correct. It's like the best thing in the world. But one little thing. Oh, they've rounded it up. Okay, that's fine. I thought I got it incorrect. So yes, I got it correct. So it takes 1.77 times 10 to the minus 5. Okay, so I got it right. Okay, that's the answer. I'm so proud of myself, honestly. Oh, that's good. Calculating relative atomic mass. Now, the relative atomic mass quoted on the periodic table is the weighted average. Oh, I actually need to remember this as well. Okay, relative atomic mass. Okay, this is how I remember it. The relative atomic mass is the average mass of an atom of an element relative to 1/12 the average mass of carbon 12. So this is a new title actually. Okay, now we have this beautiful thing, which is called a spectra. So I'm gonna actually draw it out. This one's actually quite easy, this stuff, so I'm not gonna worry too much about it. Percentage abundance, and then we've got like say 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay, because it's always, because it's a percentage, it's gonna be out of 100. We have like 24, 25, and 26. This is the M to Z, which is the mass to charge ratio. Then I'm just gonna make these lines. I'm gonna make it like 78, 10, and 11. Kind of in line with 20, but it's fine. So 11.17%, 10.13%, and 78.70%. Now this is magnesium 24, magnesium 25, magnesium 26. If asked to give the species for a peak in the mass spectrum, then give charge and mass number. Okay, now what we have to do is the isotopic mass. Isotopic mass, well, this is the the sum of the isotopic mass times by the relative abundance, and then it's divided by the total relative abundance. So for example, in this case it will be just so the example would just be to in bracket altogether, 78.70 times 24. And then we add that to the next peak. So it's going to be like 10.13 times 25, add 11.17% times by 26. And then it will be all divided by 100 because the percentages are out of 100. So all divided by 100. And what we get at the end of this is 78.70 times 24, add 10.13, 10.13 times 25, add 11.17 times 26. 26 equals, and then I have to divide it by 100. So for the answer, I'll get 24.3247, but I'm just going to give us 24.372. Wow, I actually got it right as well. But yeah. Okay. But then sometimes it's different, isn't it? Relatively. Oh, whoops. I've written the wrong thing now. But in this case, it's 100. Okay. Oh, that's a nice question. I'll print that out too. But it's just simple. Like, for example, calculate 124. I have to do 124 times 2, add 126 times 4, add 128 times 7, add 130 times 6. And then you divide it by what 2 plus 4 plus 7 plus 6 is. So if I just calculate this, so 124 times 2, add 126 times 4, add 128 times 7, add 130 times 6. This all equals to 2,428. And then I have to divide it by 2, add 4, add 7, add 6, which should be 19. But what I get in the end is 127.79. I'm gonna round it to 79. Oh, I could have just done 8, but it's fine. I still got roughly the same answer. So I just realized I didn't leave enough space. It's like this tiny space. Okay, so I'm done with that. Oh, this one's a really bad one. I actually really hate these ones. Okay. Let's get another page out. Okay. I'm gonna print that out too. Okay, copper has 2 isotopes. 63 and 65. The relative mass. So in this case, we actually have the relative atomic mass. So we do 63.5 equals, and since we know because it's something, well, what is it called again? It's the isotopic mass times the relative abundance. So we have to do like something. So we say x times 63, and we add that onto something, which is x times 65. Why is it 1 minus y? Oh. My brain right now, what is going on? I actually don't understand. 63.55 equals 63y. Okay, so 63.5 equals 63x in this case. Plus. I just don't understand where the 1 minus y came from. 1 minus y. Okay. I'm gonna do the rest, and then I'm gonna figure out what happened here. I'm gonna make a bigger. Okay. Still one I need help with. Okay. Chlorine has two isotopes, 35 and 37. These lead to the following caused by diatomical molecules. So, relative abundance, 35, 35, like 72. 72 and 74. Why does this have to look so confusing? The 160 peak has double the abundance. I shouldn't ask. Check what's going on. Yeah. I just copied it and it's not in there. Where's it gone? It's not even here. Oh my gosh. remember this one time. Oh, I think I remember. Okay, that's just the neutrons. Okay. Measuring the amount of a molecule. Okay, I've done 43 minutes of studying right now. So I'm going to take a 5-minute break and then